I want to do a video here, basically explaining the last news release in more detail for people who are interested in basically taking it to the next level, doing a deeper dive into what this geological model means, what some of the implications are, and maybe how it changes the company's confidence in its drill targeting moving forward. And so the release itself had a series of 2D plan maps and figures, but the problem with the news release is you obviously can't embed video. So the video here is intended to look through the model in 3 dimensions. So for one, we're going to actually get to spin it around and see how it actually looks in 3D. But then we're going to talk in detail about how it was developed, because I think it's important for investors to get some confidence or at least understand what the confidence in the model is, because that's going to equip you to make investment decisions better based on the probability of the model being accurate, the model being correct, and of course, if it is, what the implications of that are in terms of what the potential size of Leviathan could be. So we're going to open Leapfrog, and we're first going to basically talk about what the inputs were to the model, which are essentially all of the drilling that we've done ever since making this blind concealed discovery in 2023. So what those inputs were, how they were used to construct the model. And then we're going to look at some other layers of data which weren't used at all to construct the model, but actually end up correlating almost perfectly with the model itself. Like some of the geophysical and geochemical layers, just happen to spatially coincide and sort of increase the confidence of the model. And then kind of finally, we're going to look at, okay, we've sort of evaluated what the confidence of this model is, how accurate we feel it is, what are the next steps, and what does it mean, what are the implications in terms of the potential value, if it is correct, and if it will expand in the way some of these other data layers suggest it will. So with that said, let's jump into Leapfrog here. Okay, so figure 1 was basically a plan view looking down, and I showed the Leviathan porphyry, which is the porphyry center we have drilled so far. And so the crux of this model and this release is basically we have gone from an initial discovery at the end of 2023. It was a blind discovery. Okay, so this is a concealed deposit, and the hardest thing to do is figure out where you're going to drill next after you've drilled your discovery hole, because you have no idea what the geometry of that system, that blind system, looks like. You don't know which way it's trending. You don't know which way it's dipping. You don't even know what part of the system you're in. So pretty much all of 2024, which many people know was a challenging year for the stock, was basically spent figuring out the system. And we had to do big step outs. We had to drill all kinds of different targets and different anomalies in different directions. And really what that's all culminated in here is allowing us to actually model the system and model the mineralization. And fortunately, we used oriented core, which allows us to do that with a very high degree of accuracy and precision. And so now that is behind us, now that we were able to do that, the boring part is over. And now for me comes the fun part of actually testing the model, because if this is correct, if the model is right, it's off to the races. Now, I don't think the model is going to be perfectly accurate. I think it's probably very, 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 very close. I think it is absolutely northeast southwest trending. I think it's southeast dipping. But step number one with some of the first holes we're drilling, hole 1 and hole 2 here, are this is between two holes that were drilled last year. It's a gap in the model, and it's drilling to the northwest, as is hole 2. Hole 2 is actually a step out, but we're going to start by filling in the gaps, getting the model 100%, and then we're going to start stepping out from there. So with that said, let's jump in a leapfrog here and talk a little bit about how the model was created. So what you're looking at here is just a plan view. We're looking straight down, north is up. These are all of the deep holes that we've drilled basically in 2024 and the end of 2023. So these are all the holes that made it through the cover into the Triassic. And the first step was we wanted to model the geology. Second step is we're going to model the mineralization. And so to model the geology, we did it in detail, but for the purposes of this video, we're going to simplify it into two groups. You've got what we call the host rock, which is pre-mineral. It was there before the porphyry showed up. And these are bedded, stratified, volcanic rocks, a few sedimentary rocks, but mostly volcanic rocks. We call that the host rock. And then you have the porphyry. That's what intruded in as a magma. It injected in to these host rocks and shot copper off in all directions, copper and moly. So what I've done here is what you're looking at is the places where porphyry, we call it quartz porphyry, was logged in each of the drill holes. Now, first we log it in the field. Then we get our assays back and we log it again. And then we log it a third time based on, just kind of refining everything with assays and core photos and a bunch of other data. So this is like really, really highly confident lithological logging. So what you're seeing is a bunch of hole traces. And these red sections are where we intersected porphyry, where we're very, very, very confident that we've intersected porphyry. Now the quartz porphyry is a very obvious unit, so it's not that difficult. So the next step is to model this. Now, how do you model this? You got to connect basically everywhere that porphyry was intersected in these holes. You got to connect them together, and to do that, you need to know which way it's dipping. You can't just go connecting dot to dot. It just doesn't work like that. And fortunately, I think I mentioned earlier, we drilled with oriented core. And so what that means is down the holes, we can actually measure the real true strike and dip of anything planar. And so this represents all of the measurements that were taken, thousands and thousands of measurements that were taken, down almost all of the holes. And this is a list of all the different structures that were measured. Now, the important structures were the contacts of the host rock and the porphyry. So we either called it contact or we would have called it intermineral porphyry. These are the important features. And this basically tells us what the orientation of that porphyry is to drive the modeling of it. And I'll just show kind of one other key thing. Long story short, it's southeast dipping. And pretty much everything here is southeast dipping. And, I'll show you kind of an example of how we determine that, because nothing in geology is perfectly consistent every single time. And so you have to sometimes put these things on what are called stereo nets, which is what we're looking at here. And so this is a great example. This is basically, porphyries have 4 or 5 different sets of veins. You got, these early halo veins, which bring in the copper. Then you got your A, B, and C veins, which bring in copper. And then you got D veins, which are late and are kind of pyrite only. So if we just take the veins with copper in them, the early halos, the A's, the B's, and the C's, and we throw that on a stereo net, what you're looking at here are poles to planes. we can contour the poles to the plains, and where they all cluster is in this northwest quadrant, which tells us that all these poles represent southeast dipping plains. So basically, when you contour anything at Leviathan on a stereo net, everything clusters in the northwest quadrant. Pretty much everything is dipping to the southeast, whether it's copper veins, whether it's porphyries, all kinds of different features are dipping to the southeast. And so we use these stereo nets because they're a really, really good way in porphyry systems where things are highly erratic and they kind of stockwork, all over the place. But if you collect enough data, hundreds and hundreds and hundreds of measurements, you'll see that they start to cluster in areas. And when you see that same clustering in multiple different features, right? Veins and dikes and everything, you get a pretty high degree of confidence that you're dealing with a system that is dipping or plunging to the southeast. And the same goes for the volcanic stratigraphy. It's actually dipping the other way. It's dipping to the northwest. Because when a porphyry intrudes, it intrudes vertically. So it's a vertical thing intruding vertically into horizontal stratigraphy. So if you tilt that horizontal stratigraphy to the northwest, it's going to dip northwest. But that vertical thing that intruded it is going to dip the opposite way, right? It's going to dip to the southeast. And so everything we're seeing, because everything in a porphyry comes in vertically. So when you tilt something vertical to the northwest, it's now dipping to the southeast. And so enough about that. Let's get back into it. So let's now bring back up those porphyry intersections. We know they're dipping southeast. So we take all this information, we send it to our modeler Wojtek in Czechoslovakia. This guy is just a absolutely wizard when it comes to geological modeling. We've used him since 2022 when this was just a silver system. He had that modeled out beautifully. And you can see these are all the different units he's modeled. But again, we're only focused on one thing here. We're only focused on the porphyry, right? So I've styled it in white here just for some contrast with some things we're going to show later. So southeast dipping, right? So what are we doing? All we're doing is we're connecting all these intercepts of porphyry. We're connecting them into one continuous body and something that's dipping southeast. And this is what it looks like, right? And this is just, you look at any porphyry system in the world, you look at a cross section, this is a very, very common, kind of layout, kind of architecture for porphyry systems. And there may be multiple different porphyries in here, but we're just lumping them all in as porphyry for now. We're trying to keep this video simple. And so this is what our porphyries look like. So we got all these volcanic units that are dipping the other way, dipping northwest, and you got this porphyry or set of porphyries that are nested, and they've come in as basically dikes. Dikes are a term you use when the intrusion is planar, right? It's tabular. So you got this tabular northeast southwest trending, right? Southeast dipping porphyry dike. This is the Leviathan. Okay, so everything we've done so far has culminated in this, modeling the Leviathan porphyry. This is the culprit. This is what brought in all the copper to the Leviathan center. This is a center. This is a porphyry center, because this is where all the porphyry, this may be one, this may be multiple. This is where they all coalesced and intruded and brought in copper. So that's big, right? We actually have this now. We've got this thing modeled now. And so then the next step basically is the mineralization. So Wojtek then gets all the drill hole assay data. So let's switch over to that. Drill hole assays. And we gave him copper, we gave him moly. We also gave him pyrite, right? We've logged percentage of pyrite, which you can also do from assay data, iron and sulfur and copper, and given them that information as well. So what we've done is we said, Wojtek, okay, the copper is obviously southeast dipping as well. We know this from the stereo nets going back to the oriented core data. and we know it's occurring in the host rock above and on the sides of this porphyry. So the high grade is basically surrounding the porphyry as a shell, and it's southeast dipping. Model that for us. And so what does that look like? Boom. So there you go. Obviously, the warmer the colors, here's your legend here, are the higher the grades. It's a really nice model, actually. And I won't get into it in this video, but this is the copper shell. The moly shell fits pretty nicely with this as well. But there's a pyrite shell as well, and it sits outboard on either side. So it really is, a perfect porphyry system. It is a very classic porphyry system. You've got a central porphyry intrusion, which is low grade. And so this brings up another thing, which we might want to get into in another video, because there's different types of porphyries. Some porphyries you want to target the very center. Sometimes the high grade is in the potassic alteration of the very center. It's starting to look like maybe at Leviathan, now that we've modeled this, now that we understand this, we're less interested in trying to target a potassic center here, because it looks like we may have found the potassic center, at least with this biotite alteration in the porphyry, and it's low grade in the porphyry. But around that, we've got biotite alteration in the host rock, which has been overprinted by phyllic alteration. So there's really almost no biotite actually left at all. We know that from the shortwave infrared, this work. But that phyllic alteration, that phyllic overprint, has brought in a lot of copper. And so it's sometimes you call these things type 2 porphyries, and there's all kinds of details we can get onto that. But the really, really high grade stuff is focused around these sort of shallower parts above the top of the porphyry system. This is the high grade. Sometimes you call it an inverted cup model if it's a kind of conical intrusion, and the ore shell forms like an upside down cup over the conical intrusion. But this case, it's a dike shape, and so we've got what we call the hanging wall, which is on the high side, and the foot wall, which is on the low side. And that's how we basically categorize the mineralization so far. So pretty nice model, hangs together well. Central, porphyry intrusion, low grade, nice copper moly shell around that, and then of course not shown, but these outboard holes have very, very, very high sulfur, and actually I'll give the reason I'm not showing it is I don't have it preloaded in here, and I don't want to go digging around for it. But if I just show the sulfur assays, I mean, it's pretty obvious. Sulfur, iron sulfide is pyrite. We don't have a lot of, sulfur, we don't really get it in anything else here. Like sometimes you get anhydrite, which has a lot of sulfur. We don't get that here. So if you see high sulfur, it's telling you pyrite. And you can just see so clearly those high sulfur values, those high pyrite values, just sitting on the outside of the ore shell. So we've gone from this really kind of complex, scratching our heads, we're going to test this anomaly here, this anomaly here, and you got this zone, and, hope for the best, kind of a tough pitch, to this model actually hangs together really well. It's actually just, a very, very typical porphyry system. And the only, sort of nuance with this is that, the high grade, this is the type of porphyry system where at least it's looking like the high grade is in the phyllic. And, we'll get into this more on a future news release, but, the higher you go, the shallower you go, it seems the higher the grades get. And so, of course, this here is the, there's an unconformity. So this is basically the cover. So you've eroded where we've drilled, you've eroded down to, really, really the high grade part of the porphyry system. And we'll talk more about, how we're going to track some of this high graded, we call it the enrichment, more in a future release, basically. But this is your primary mineralization for the most part. This is a porphyry system. It's looking good. So this is what we received from the modeler. He didn't get any geophysical data. He didn't get any other data other than, the lithology and the oriented core measurements, and that's how he modeled it. So, a couple things that really give us a lot of confidence. There's all these kind of light bulb moments that happened when he delivered this model, and we start turning on other layers that we previously interpreted a different way, and all of a sudden they just make so much more sense now. So we'll start off with, I just want to show the chargeability. I'll rotate this around so you can kind of see what this looks like, and you can see, boom, there's a lot of open stuff over here. There's a lot of expansion potential, and the first two holes, actually, before I move on, maybe I'll show the first two holes we're drilling this season and kind of why we're drilling them. HW3, hanging wall 3. Basically, we created a series of 400-meter spaced fences, and we're drilling 200-meter centers, 200-meter pierce points on a grid along the hanging wall and a grid along the footwall. And we just decided that we're going to start with hanging wall 3, HW3, because as a first step, obviously we're quite confident in this model, but let's really give ourselves confidence by testing it with the first two holes. So we're going to go in between 2420, which is one of the only holes we've drilled to the west, and 2419, which was drilled southeast. Now, most of our holes were drilled to the southeast, which is a terrible direction to be drilling when you realize that your porphyry is dipping to the southeast. Because unlike maybe a high-grade vein system, you can't just drill down dip and expect that you're going to get higher grade. Porphyries are homogeneous, right? They're big bulk tonnage systems where the mineralization is very even throughout. So either, you're drilling right down it and you're getting homogeneous grade, or you're maybe drilling right down the center. And you're drilling down, the low-grade center, or you're drilling outside of it. So in other words, you're either hitting or you're missing. Whereas drill northwest with a long enough hole, you should hit. So assuming this model is reasonably correct, which we have a very high degree of confidence it is, the hit rate should go way up. So what we're going to do with HW3 is obviously hopefully confirm this model, knock on wood, step it back, and try and get the full width, because we've been drilling parallel with the system, we don't have holes that go across it, so we don't know how wide this is or how wide this is. It's very difficult to model when you got holes like 2419 that are going straight down it. And so you got this little narrow looking section of hanging wall here because 2419 went straight down it. So you can only model a little buffer on either side of it. So HW3 is going to come in, and we're going to figure out, hopefully, how wide this hanging wall really is. Probably shut it down in the porphyry, but you never know. We might end up going all the way to the footwall if things are looking good. Hole number 2 is footwall 3. So we got hanging wall 3 and footwall 3. And this is just stepping out to the northeast of the footwall. So we're actually starting with a step out because we got a lot of drill holes. They were all subparallel, unfortunately, with the hanging wall. But because we've got enough holes in there, we're confident enough that we can actually start with a step out in the footwall. And so that's what we're going to do with footwall 3. Try and actually catch a little bit of hanging wall and then go through the porphyry and again capture the full width of that footwall. Again, our 2412, one of the best holes we've ever drilled as well, ended in pretty good high-grade mineralization at depth, and it was drilled right down it. So let's try and figure out how wide this thing actually is. So that's what the plan drilling looks like so far. What's the blue sky and how confident are we in this model? So we'll look at the chargeability. And this, again, that's the old chargeability. We reprocessed it. Barrick's geophysicist works with Newmont's ex-geophysicist, and they cleaned up an issue we had in the data called EM coupling. and reprocessed it and ran new inversions. And so this UBC model is like a really, really cleaned up version of the chargeability. And so this is, you know, the most accurate model you can get. And so when we overlay chargeability, which chargeability is just measuring the amount of disseminated sulfide in the ground, you see a remarkably good correlation with the mineralization that Wojtek modeled, based only on drill hole assay data. So if I spin this around, let's turn some things off so we can kind of get a better view here. Turn off the porphyry. Right? Look at that correlation. Even the chargeability is dipping southeast, and you can even see there's like a hanging wall side and a footwall side to the chargeability, right? And you can see it's kind of a divot in here in the center where that low-grade porphyry is, that low total sulfide porphyry is. So the fact that it's correlating so well with the chargeability, which was modeled completely independent of, is a pretty good sign. This is a really, really good sign. This is giving us a lot of excitement and confidence now. Okay, so here's where it gets even more interesting. The chargeability, and let's start by looking at, okay, what does the whole survey look? There's what the whole survey. Let's zoom out and see the whole survey from surface. Now, what I can do is I can filter the values. So I can say, well, I don't want to see the low chargeability. Show me only the high chargeability. I can slowly drag away the low values. And you'll notice here, look at the north end of the survey and the south end of the survey. The high chargeability extends all the way to the north end of the survey and the south end of the survey. So we've got a 4 kilometer long chargeability high I'm about to show you here, but we don't know how long it is because we haven't surveyed large enough. And so that's why we're expanding. That's why we're doing more geophysics this year, because we need to go bigger. And again, that's something we'll talk about in a future release, but just know that this is still open. And so let's drag this away and let's see. Okay, so let's see just the really, really high chargeability. This is 4 kilometers. It's bent, which is another post-mineral feature here, that everything got kind of a little bit folded, just very gently open folded. But what this is telling us, and by the way, we can even look quickly at the surface geology and how well this matches the surface geology. So as you can see, this is high, detailed mapping that's been done over 3 years at Hercules. And as you can see, the Jurassic rocks have this big, giant, gentle, open fold. Wraps around like this. Let me just actually slowly bring that away. And you can see with the chargeability, it's got that same gentle folding. Now, this chargeability that we're looking at, this is only, down in the Triassic, right? The overlying cover rocks, as you can see in the top of these hole traces, that don't have chargeability. There's not much sulfide in the Jurassic at all. So the fact that the Triassic, the chargeability is folded in the Triassic the same way we see the Jurassic rocks folded, tells us that this porphyry system was in place northeast southwest as we've modeled it, but it's been folded, it's been bent. So there is a bit of an arcuate shape to the whole system now. This dike, this system of porphyry dikes was gently folded. So right now we've got a 4 kilometer long chargeability anomaly open on both ends, but we've only drill tested 1.6 kilometers of it. So from here to here is 1.6 kilometers. And that's all that's been tested so far. So you can imagine, obviously we're encouraged at how well these two correlate, how well the modeled mineralization correlates with chargeability completely independent of each other. And then, assuming that the drilling is able to confirm the accuracy of this model as well, you can obviously see a path to growing this thing to pretty significant scale. If all 4 kilometers of it are the same or better, this is going to grow pretty big, pretty fast. The other thing, in terms of geophysical coincidence here that we'll just look at is the mag. And we've never press released the mag before. And I'll tell you why. So again, here is the geology. This is how it's been mapped. It's been mapped in detail. We've mapped this thing 2022, 2023, 2024. I mean, 3 years of detailed mapping on surface. This is what the Jurassic looks like. It's folded. Now, we flew a drone mag survey in 2023 before we even made the discovery, and this is what we got. So it didn't matter. Now, at the time, we were exploring for silver, and we were only, we flew this really, really detailed 25-meter spaced drone survey to try and get really high resolution structures, trying to figure the epithermal silver system in the Jurassic. And we didn't see anything. There weren't any faults. There weren't any lithologies, right? Like flipping back again to the map, right? Like you can see the faults around it. There's nothing that matches that. And so we got the drone mag results, and we couldn't figure it out. We scratched our heads. It's never made sense, and we just kind of forgot about it until very recently, until we got the model back. And we got the model back. So for 2 years, it sat on the bench collecting dust, not making any sense. Now we get the model back, peel it away, right? Let's turn on that porphyry again. It all finally starts to make sense. Right, so here's that porphyry, northeast southwest trending. You can see it right there. Bring that mag back on. There it is. So the mag, it turns out all along, all this detailed stuff that we're seeing in the near surface that was going northeast southwest, this is reflecting the Triassic geology. So the mag is actually seeing deep. It's seeing below that non-magnetic cover, because the rhyolite has no magnetic minerals in it whatsoever. So it's a non-magnetic cover. And we're seeing basically the Triassic geology, which is northeast southwest trending in the mag. And it matches perfectly with the model, matches perfectly. So again, just another layer of confidence that the model is not only correct and accurate, but the system is open. I mean, you can see, the mag continues unobstructed across Great Creek. This is a major lineament. I've always worried that there might be a major structure here, right? Maybe a big hard stop to the system, and that 4-kilometer chargeability, which we've only surveyed up into Great Creek, we're going to try and extend it. Maybe it won't extend, but just seeing that mag extends across the creek uninterrupted, there's no post-mineral offset showing or suggested, that's a good sign. That's a good sign that this thing is just going to keep on going and keep on going. And we've got this big expanded land package now, so we're just going to have to see how big this thing can get. The last thing that I'll show, in terms of model confidence is, we've shown the 2 geophysical data sets. We've seen the chargeability matches perfectly with the mineralization. We've seen the magnetics matches perfectly with the porphyry system, the lithology, which has a little bit of magnetite in it, and that's why it's reflecting on the mag survey. But the third thing that correlates with the model is the surface geochemistry. So look at this. I've just outlined the porphyry in black. I've outlined the mineralization in red, taking it away here. We've got hundreds and thousands of soil samples that we've taken on surface, and hundreds, 700 some odd rock samples. And when you contour them, just with a computer software, you can clearly see the copper moly mineralization, where the system daylights at surface in this erosional window into the Triassic, is northeast southwest trending. So here we go. Another thing supporting that we've got northeast southwest trending porphyry system here, right? So right now, if we were to kind of summarize this, what's going on here is we've got one porphyry center already defined, and we call this the Leviathan. And the Leviathan, before we had this model, we sort of had all these different zone names. Well, Great Creek Zone and the Southern Flat Zone are really now all part of one thing. I almost don't even want to use separate zone names for them anymore, because if we flip back to the chargeability, this is all just one thing. This is Great Creek up here. This is Southern Flats down here. In fact, we actually see the chargeability get stronger on either side of where we've drilled. We know there's better host rock in this area. That's highly encouraging. We know that the system is tilted to the north, and therefore shallower parts of the porphyry system we might be able to expect in here, which is where we see the higher grade phyllic alteration, the better alteration in the shallower parts of the system up here. So there's a lot of optimism for expanding the Leviathan Center. And we've also got 2 conceptual targets that we're going to be testing as well. So obviously priority number 1, expand the Leviathan. We're going to start off with the first 2 holes confirming the model. Fingers crossed. If we can confirm the model, we are going to start stepping out on the model. We're going to be drilling northwest to capture the actual full widths of the mineralization. We're going to see how far it extends to the north. We're going to see how far it extends to the south. But we've got conceptual holes planned as well, because there may be additional centers here. We know that there's one down to the southeast on Cuddy Mountain. We may have 2 more immediately adjacent to Leviathan. We may have 3 parallel porphyry dikes all in a row here. And the second one is potentially represented by something we call the Western Deeps. So the Western Deeps is a big chargeability anomaly, obviously perfectly parallel with the Leviathan anomaly. And it's never been drill tested. We've tried, but the problem is it's down dropped. It's a challenging one. So there's a fault we call the BNA fault, and we know from drilling on either side of it that the Jurassic stratigraphy gets dropped down about 300 meters to the west. And so the cover is really, really, really thick over this target. So we're estimating it's going to be about 1,000 or 1,100 meter hole to get down to the Western Deeps. And this is the first hole that's going to test it. We like shallow. We like testing shallow parts of the system. And since all these porphyries are tilted to the north, we're going to go for the north end of this anomaly and hope that we're going to see some phyllic alteration and some shallow, maybe even advanced argillic alteration, which is where the high grade concentrates in these systems. More on that in a future release. So the Western Deeps is a really interesting target. And we're just going to have to cross our fingers and hold our breath with a conceptual hole here. But the parallelism, the strength of the anomaly, which I'll show you here as well. So getting back to that strength filter, if I keep going, if I keep pulling away lower values, you can see the highest values now are only in Southern Flats and Great Creek. There's a couple blebs still here where we've drilled. But the Western Deeps doesn't go away. It doesn't go away. So if we keep going up, keep going higher values, show me higher, to the point where we're now above everything in the Leviathan. We're now higher chargeability than everything in the Leviathan. This is what we're looking at. So all of this here represents higher chargeability than anything in the Leviathan. So I'm pretty excited to drill this thing. No idea what it is. But whether it's porphyry or just something boring, at least we're going to find out. The other interesting target, conceptual target, is the eastern block, which is not really represented by a strong chargeability anomaly. And that could be due to a number of reasons, but there's a very, very, very strong geochemical anomaly at surface. And we have mineralization, we drill mineralization very, very, very close. If we flip over here, 2420, I don't know if I have, let's see, 2420 was the shallowest we've ever hit mineralization. And that was this hole right here. So we're very close. And again, northeast, southwest trending, you've got very, very high grades sampled on surface here. But we know it's different. We know it's not Leviathan. We know it's not centered on this porphyry. So it has to be, if there's anything here, it has to be centered on another porphyry. And so we've planned many more holes because obviously it's a shallower target than Western Deeps, which only so far has one hole. We got 1, 2, 3, 4, 5. We've got a skarn. We got the big cut skarn, which is a super exciting high grade target in itself, which has to do with really, really good host rocks. So hopefully that was helpful for investors out there who just like to have more information, like to do a bit of a deeper dive on their investments and try and assess what is the probability of success here in this upcoming 2025 program, because that was something that was very hard to assess in 2024 when we just made a blind discovery. We had no clue with the geometry or architecture. We had no idea where we were in the system or where it was trending. All we could do was say, okay, we got a bunch of interesting anomalies here and there. We're going to be testing them, but you can't assign probabilities of these targets hitting. And so now you can look at this as a model, right? And what do you think the accuracy of this model is? How likely is this model to be, reasonably accurate, reasonably correct? And from there, if it is, then, how likely is it to be, are we to be able to expand from 1.6 kilometers to maybe more like 4 kilometers, the total length of that chargeability it's correlating with. And of course, we've got the MT survey and NSIP survey upcoming. And what is the probability that that's going to expand even further, maybe upwards of 6, 7, 8 kilometers. So drilling's coming up soon here. Hopefully the next update is that the drills have mobilized, and from there we're going to be looking at starting up this geophysical survey very soon here, and then talking about some of the secondary enrichment. So this video is really sort of focused on the size potential, I would say, in terms of what the model's showing so far, and what the potential size expansion can be, right? So in terms of length, width, and depth. But then, we didn't really touch too much on grade. But we did mention that, we're seeing much higher grades in the shallow part of the system, kind of above the porphyry. There's a release coming up, which is going to get way more in depth on that, and kind of gets into a recent study that was done, which shows some very, very, very important implications about that high grade enrichment that's focused in the shallow parts of the system. So again, hope these are helpful. Stay tuned for the next release, and hopefully another video explaining that one as well.